Hello everyone. PostgreSQL AI capabilities. AI companies are paying thousands per month for Pinecone. I am going to show you something that is going to make you a question every year and every vector database subscription your team is payable for. This query right here, semantic similarity search across 10 million product embeddings. So 10 milliseconds response time. As a transaction, SQL joins and it runs entirely inside PostgreSQL. No pinecone, no wave data, no chroma. Just PostgreSQL with the pgvector extension, which is free and open source. In this video, I am going to walk through every major AI capabilities that PostgreSQL can handle natively, step by step with working SQL you can copy and run right now. So just understand that what is Pinecone and the pricing model. Understanding the cost of the Pinecone and pricing model for the usage of the vector search and PG vector. Minimum usage for the standard and enterprise pricing plans include monthly minimum usage commitment, that is plan starter, standard, and enterprise. Beyond the monthly minimum, customers are changed for what they use every month. Example, usage below monthly minimum, users exceed monthly minimum. And also prepaid cards, credits, and the serverless indexes. With the serverless indexes, you pay for the amount of data stored and operations performed based on the three usage metrics: read unit, write units, and storage. So read units, it is for measures the compute IO and network resource consumed by the following read records: query, fetch, list. And the query, it is used for the namespace size and read units per query. It is, say for example, less than 0.25 GB, it is 0.25 RU minimums. 1 GB, it is 1 RU. 10 GB, it is 10 RUs. Likewise, 100 GB, it is 100 RUs. For fetch, request uses 1 RU every 10 records fetched. For example, fetched records, um, fetched records, it's 1 RU. 50 fetched records, it's 5 RU. 107 fetched records, it is 11 RU. Kind of, this is the write units, upsert, update, and delete. And this is for upsert. This is the pricing model for upsert and update. This is for that KB per KB and wise previous record and Ws. And delete, this is for the record per batch and dimension and also average record size Ws. So storage perspective, storage costs are based on the size of an index or per gigabyte GB monthly rate. The size of an index is defined as the total size of its records across all namespaces. For the latest storage pricing rate, see pricing model here. Okay. So how it will be calculated? The calculated dense index size assuming no sparse vectors. Index size equal to number of records int ID size plus metadata size plus dense vector dimension at 4 bytes. This is the calculate dense index size. For example, dense index calculation, these are all the examples like records 5 lakhs, it is dense vector dimension 768, average metadata size 500 bytes, and index size 1.79 GB. So these are all the pricing model, and it is for SQL query and semantic search on PostgreSQL. And coming to this PostgreSQL AI capabilities, what we are covering and prerequisites required for this And of course, welcome to AI DBA Hub. I am your host, and today we are going to a complete walkthrough of PostgreSQL AI capabilities. We are going to cover 8 capabilities like vector embedding storage, semantic similarity search with HNSW indexing, full text search, fusing matching with pgtran, building a complete RAG pipeline in database ML with pgml, hybrid search combining all retrieval metadata methods and vector analytics. By the end of this video, you will have a complete AI retrieval stack running inside your PostgreSQL database. Let me start with a setup. Okay. So first, um, that AI PostgreSQL AI capabilities. That is, we are going to see pgvector semantic search, RAG pipeline, full text fusing in DBML hybrid search. So your AI capability PostgreSQL can handle natively simulated step by step with live execution here. So vector visualization and semantic search demo, no separate vector database needed. So in this case, I am using PostgreSQL 15 version of the database. Okay. So number one, AI capabilities. Number one, PG vector setup. So coming to this PG vector setup, capability number one, vector embeddings with PG vector. Okay. So this is having 384 vector type and embedding storage and also Python pipeline. So 384 vector types, dimension 384 vector types, dimension all in mini LM L6 version 2. Okay. And also 1536 dimensions for OpenAI ADA02. And it is less than 1 millisecond vector similarity lookup using HNSW, and it's completely free of cost for the FastPG vector extension. So you can simply install free of cost that which is your PostgreSQL 15 version of the database is running, that AI capabilities and PG vector extension you can install with the free of cost. Okay. And coming to this, what a vector embedding looks like. So embedding vector looks like it is the below order with more than 352 more dimensions. It is available. So, so uh, we are going to see the PG vector extension how to install. So it is free of cost, as I said, right? And you can create an extension if not exist, like create extension if not exist vector, create extension if not exist pg underscore trg. So first we need to install the pg vector extension and PostgreSQL running on your database, and then you can create a table with the vector column. You have to create a table with the vector column. Create table products like you have to create, and then verify the vector column. So you have to verify your vector column. So I will run this query, and this you can see here. I will show you the demo here. So if I run this, it will create. You can see create extension if not access vector, and create extension if not access pg underscore trm. So create extension completed, create extension done, and then create table name, create table also completed, and also we can see that preview of this vector column. So this is what it's showing like. So select ID, name, dims preview, like on that is ID, that is the wireless noise cancel headphone 384 embeddings. This is a vector embeddings. As I shown you right earlier, this is a vector embeddings, right? This much dimension available, right? So you can see here ID, name, dims, and previews. So it is showing PG vector active 384 dimensional vector stored alongside relational data. Okay. So here I will give you a quick setup tip. First, you need to install pgvector with sudo apt install PostgreSQL 16 pgvector or Ubuntu or any other Linux, or brief install pgvector macOS. No separate database needed. Okay, so you can install the pgvector along with the PostgreSQL 16 pgvector. And there is no separate database needed. Your existing PostgreSQL becomes an AI native vector database instantly. Generate embeddings with sentence transforms free or OpenAI API, then insert the float array as vector. Okay, this is the quickest setup tip. Okay, while you are installing the PG vector setup, you can install directly from the PostgreSQL section PG vector. You no need to install it separate database. It will take it. Okay. So your PostgreSQL database becomes an AI native vector database instantly when you are setting up like this way. Okay. So this is the first AI capabilities we have seen, right? So the storing embeddings, that capability PG vector, storing vector embeddings in PostgreSQL. A vector embedding is a list of numbers that encodes a semantic meaning of text. Two pieces of text with a similar meaning will have embeddings that are mathematically close to each other. pgvector adds and vector data type, which lets you store this list of numbers as a regular column alongside your normal relational data. So I'm going to create a product table with a vector 384 column, right? So I shown you here example, right? And show you that Python code generate embeddings with the free sentence transformation library and then insert first bridge of vector. So I show you a simple demo here. If you want to put that live, let me connect to that Postgres SQL database. I so here the Postgres SQL 15 is running. So I am going to connect this database Postgres and PSQL -u Postgres. Okay, so I connected and simply I wanted to look what are all the databases running. So here that by default databases are running, and I already created one database name called AI DBA Hub, and let me connect the database AI DBA Hub. Okay, so I connected to the database called AI DBA Hub. Okay, so here, okay, I am going to create that extension. I'm going to PG vector extension. I'm going to create, right? And let's say so create PG extension if not exist vector. Okay, that is I'm going to run. Extension vector is not available. Detail could not open extension control file. User PSQL share extension vector control. No such files or directory. Hint, the extension must be first installed on the system where PostgreSQL is running. Okay, fine. We need to install that PostgreSQL extension. Okay, all right. We'll install. See, we have seen here, right? So we need to run like this. For my case, the database it is running. So let me install that PostgreSQL 15 pgvector. And I'll show you that live demo in my next video. It is uh, interactive demo I generated, right? So this is how that create table, that the products it is working, how that vector database embeddings is working. So I shown, right. So this is the PG vector. This is a capability number one. Okay, and coming to that capability number two, that semantic search. Semantic search similarity. It is using HNSW index, cosine distance, and less than or greater than or equal to operator sub 10 milliseconds at 1 rows. So these are the key features in the semantic similarity search. Okay, so how it is working? HN, SW index and distance operators. This is how it is working. Capability number two, it's semantic similarity search. Three distance operators, cosine distance using less than or greater than or equal to operator is what you want to text. Equivalent distance using greater than or less than or is good for images. Inner product using hash is equivalent for normalized vectors. I am creating an HNSW index and hierarchical navigable smallware, which is the state of the art approximate nearest neighbor algorithms. The difference between HNSW and brute force search is 50 milliseconds versus 80 milliseconds at 1 million rows. Let me run a semantic search for wireless audio with long battery life and show you what it is finds, including products that do not contain any of those words but semantically similar. Okay, so here you can see that semantic magic, the find meanings, not just keyword. A search for noise cancelling audio semantically matches ANC headphones even though zero words match. The embeddings of both phrases is mathematically close in 384 dimensional space. Hutchins SW hierarchical navigable small world index makes this sub 10 milliseconds even at 1 million products. Okay, so here you can see that interactive demo. Distributed semantic search query, wireless audio with long battery, wireless noise cancelling headphones, it is used solely, and Bluetooth over ear headphones and ANC, solely 2.94 seconds and 0.91 millisecond. True wireless earbuds, that is 6-hour total play, it is showing 0.87 millisecond. Portable Bluetooth speaker 20-hour battery 0.79 millisecond. And USB-C audio adapter, this showing 0.40 second, and laptop stand ergonomic, it is showing it is 0.1 millisecond. So you just make a note of it. USB-C audio adapter and the laptop stand appear with low similarity scores. The model correctly determines they are not semantically close to the query. No keywords matched, yet the top 4 results are all relevant audio products with long battery life. Okay, these two it's not relevant. Okay, the USB-C audio adapter and laptop stand ergonomics, it's not a relevant match. And other 4, the results are relevant audio products with long battery life. Okay. So here I am coming up with that live interactive demo and what it is doing. Step 1, create a HNSW index, state of the art AN. So first you need to create index in products HNSW on products using embedding vector cosine orbs with milliseconds 16 of construction of 64. And then you have to make a note of it. M equal to 16 connection per node, EF equal to 64 build quality. So this is we have to understand M 16 and 64 what it is. M it is connection per node. Equal to 16 is a connection per node, and EF construction it is 64, it is build quality. And then step 2, semantic search. So we have created an index for the HNSW, right? After that, we are coming to semantic search. We are going to perform. Select name, description, price, and one my hyphen embedding greater than or equal to 0, 0.021, minus 0.043, etc. Vector as similarity from products ordered by embedding. It's a vector limits 5, right? Okay. And then hybrid vector search with SQL filter. So you are going to give a hybrid vector search, the SQL filter like select name, price, one hyphen embedding query vector similarity from products where category electronics and price between 50 and 300 ordered by embedding greater than or equal to query vector limit 5. Okay, so let me run this query. First it will create index and then it will do the semantic search, and then after that it will go for the SQL filter. So vector hybrid vector search, it is going for SQL filter. So let me run this query. I'll show you that one. So you can see create index, products index created, HNS index build, it is showing. Select name, that says it is showing that five outputs, wireless noise cancellation, and it's showing the semantic match. You can see here it is matching the semantic match. It is showing wireless noise cancellation headphones. Bluetooth over headphone ANC is no keywords match. True wireless earbuds, it is portable Bluetooth speaker and USB audio adapter and low similarity. So execution time for this query 8 milliseconds. So while we are using HNSW index and 1 million products, it is throwing the output within 8 milliseconds of duration. Okay. So semantic search working finds meaning, not a keywords. Okay. So you have understood how it is working, that semantic search. This is the AI capabilities number 2 in that PostgreSQL database. Okay. And then coming to that PostgreSQL capability number 3, full full text search. Full text search in this part. Capability number 3, full text search built in. It is doing TS vector, TS query, TS underscore rank, gen underscore index, TS underscore headline. Okay. PostgreSQL built-in NLP Capability number 3, built-in full text search. PostgreSQL had a full text search since version 8.3 and it is genuinely powerful. pgvector is PostgreSQL's way of storing pre-processed, streamed, normalized text tokens. 2 underscore TS query lets you write Boolean search expressions. TS underscore rank gives you relevance scoring. TS underscore headline gives you highlighted search snippets. GIN index makes it fast. So I am going to set up a knowledge base table with a generated stored TS vector column, which means a search index update automatically whenever the content changes, and run weighted search where title matches count more than body matches. Okay. So I am going to give you a small and simple at interactive stimulation here. So coming to this PG vector native NLP is stemming, stopwatch, relevance ranking. So no elastic search needed. PostgreSQL is built-in FTS understand languages running runs array are the same lexeme the IS at or ignored. Title matches can be weighted higher than body matches. TS underscore headline creates highlighted snippets for most application. PostgreSQL FTS replaces Elasticsearch. Okay. So here the simplest that column defined for this FTS feature how to use and purpose. TS vector generated always as two TO underscore TS vector English, comma text stored. It is used for pre-computed search index auto updates. GIN index create index using GIN. It is used for FTS underscore vector. This is what is the purpose of max at the rate queries some sub millisecond at scale. TS underscore rank. This is the TS how to use TS underscore rank. It is FTS underscore vector query as a rank. It is exactly using the purpose of relevance score for ordering results. TS underscore headline. It is TS underscore headline. It is English content query star cell equal to. So it is the purpose of using HTML highlighted search snippet. Phrase2 underscore TS query. It is used for how to use phrase2 underscore TS query English machine learning like that. So it is used purpose of adjacent word phrase search. And also set weight. It is used for set weight 2 underscore TS vector title comma A double pipeline and set weight 2 underscore TS vector body comma B. So it is the purpose of using title A greater than body B in ranking. So this is how it is using that full text search. It is built in the PostgreSQL. So I am going to show you a simple the demo in that interactive way. So first it is generated TS vector column auto updates. So first we need to create a table knowledge base ID for big serial primary key title text not null content text not null embedding vector 384 FTS underscore vector TS vector generated always as T2 TS vector English colors title colors content okay stored. So it is create index for this table. We are creating index in IDX KB FTS on knowledge base using GIN FTS vector. Okay. After that, we are doing the full text search with the ranking and highlighting. So after creating table and index, we are doing the full text search with like this way. Okay. And then we can see the result after running this query. Okay. I'm running. You can see create table, it is table created, index also created, and doing the select, right? We are doing that full text search with ranking. You can see it is highlighted. So title, rank snippet, highlighted. Intro to machine learning. Machine learning uses algorithms. Deep learning fundamentals. It is machine learning use subset. Deep ML in production system. It is using deploying machine learning models. NLP and language model. It is using machine learning for text analysis. So execution time of this query 3 millisecond. It is used for GAN index 500k documents. So that table size it's 500k documents. So in this case, FTS working with TES underscore headline snippets and TS underscore rank ordering. Okay, so hope you understand this full full text search in this PostgreSQL capabilities number 3. Okay, so coming to this capability number 4, PG capability underscore number 4, Fuse or PG underscore TRGM. So Fuse matching and autocomplete, it is capability number 4, PG underscore TRM. This is the extension that handles typos, autocomplete, and fast like queries. If it works by breaking string into overlapping 3 characters to sequences called trigrams and measuring similarity by how many trigrams 2 strings shared. Watch what happens when I search for wireless headphone, 2 typos, PGTRGM still finds wireless headphone with high similarity. Okay, this percentage operator is similarity to threshold operator. Word similarity handles partial matches. Perfect for autocomplete where you type head PH and want to find headphone. The game changer of the GAN trigram index makes like that literal patterns like that it is using the patterns queries fast. Traditionally one of the slowest query patterns in PostgreSQL. So here the PUC matching with PG underscore TRGM, it is similarity. If you are searching a word, it is using the similarity, word underscore similarity, underscore operator, percentage operator, typo tolerance, and autocomplete. Okay, and handle typos gracefully. So trigram similarity like acceleration plus fuse search. A wireless headphone, if you want to find wireless headphones with 0.62 similarity, 0 special handling in application code. PG underscore TRGM breaks strings into overlapping 3 character sequences and score overlap GAN GAS index makes like percentage patterns, percentage fast. Traditionally, the slower query run in PostgreSQL. Okay, so here you can see that the typos. Trigram similarity, wireless headphone, 2 typos here. Wireless noise cancellation, wireless ear, earbuds pro, and Bluetooth headphones over here, and mechanical keyword. So here are the 2 typos here. So let's run a quick interactive demo and that query execution, and I'll show you. So that GIS index for similarity queries. Create index IDX products for the name TRGM on products using GIS name GIS TRGM ops. Okay, and then GIN for like I like acceleration. Create index for another index we are creating. Create index for ID products description GAN on product using GAN description GIN. Okay, and then Fuse search handle typos. You can see that select name price similarity name wireless headphones. You can see the typos here. we are not completely typed incorrect words. Wireless, it is missing one yes, and a headphone, it is having also a typo. And we are giving the name like wireless headphone, it is with typo, right? SIM and products and where name like wireless headphone and order by that SIM description. Limit 5. Okay. And then word similarity for autocomplete. This is one for we are going to after creating the index, couple of index, we are going to we are doing the UC search with the handles typo and also word similarity for autocomplete. So again we are selecting with autocomplete word similarity head ph. We are typing head ph. It will complete autocomplete. So from products and where that name percentage greater than equal to head ph order by w. Yes, description no. Limit 5. Okay. Now, like with the trigram index, no head leading problem, percentage problem. Select name from products description where description like ergonomics. It is also a typo, right? So uses gen and DRM index to fast even with the leading percentage. Okay. So let me run this query and I'll show you. So it is I'm going to execute. So you can see. So first executed. It is not coming this. Okay. So it is showing that price select limitation, right? The three select already the indexes are already created, so it's not showing the index creation. But we are doing three select, right? First one, it is limiting that fuzzy search handle typos. So what we have typos here, wireless noise found despite two typos, but even though it is producing the output. Number two, we have selected for this select name that what we have word similarity, right? Autocomplete. So word similarity ph name we have given, but it is completed with autocomplete. Head ph found with autocomplete Bluetooth headphone over. Okay, it is given that. So here perfectly working for this fuzzy matching with the pg underscore trm capability number 4. Okay, and then we are coming with capability number 5, RAG pipeline, retrieval augmented generation. So that is capability number 5, RAG pipeline. The complete AI retrieval system. RAG retrieval augmented generation. This is how you build a chatbot that answer questions from your knowledge base without hallucinating. The architecture chunk your documents, generate embeddings, store everything in PostgreSQL. When a user asks a question, convert the question to an embedding, run the hybrid retrieval query I am about to show you. Take the top 5 document chunks, pass them as a context to GPT-4 or Claude and return the grounded answer. So the retrieval query uses reciprocal rank fusion RRF, which combines the ranking from vector search and full text search into a single score that consistently outperforms either method alone. Okay. So here that RAG pipeline retrieval augmented generation hybrid RRF retriever chunks chunk storage LLM context preparation. Okay. Build a knowledge chatbot. PostgreSQL as a complete AI retrieval backend. RAG architecture chunks document generate embeddings store in a PostgreSQL on our query, embed question, retrieval top 5 chunks via RRF hybrid search, pass chunks as a context to GPT, for Claude, the grounded, hallucination-free answer, PostgreSQL replaces Pinecone for the retrieval layer here. Okay. So what is the chunks ingest? Chunk docs generate embeddings insert into RAG documents, RAG underscore documents with vector plus TS vector. Retrieve RRF, embed question run vector plus FTS combined, reciprocal rank fusion, and top 5 chunks. Generate. Pass the chunks as a context to LLM grounded answer without hallucination. Okay. So here I will show you a simple demo. It is create a knowledge base with the FTS. So we are creating one dogma table or AG underscore document with the chunk text. Okay, ID because the primary key chunk underscore text not null, title text, source underscore URL text, embedding vector 384 not FTS vector, TS vector generator always has 2 underscore TS vector English classic title or chunk underscore text stored. Okay. And then for this table, we are creating index to index underscore HNSW on REG document using HNS embody vectors underscore cosine underscore apps. And another index also we are creating create index in the IDX REG FTS on REG document using GN FTS underscore vector. Okay. Finally, what we are doing are hybrid retrieval vector plus combined FTS combined. We are going to retrieve the document REG retrieval, right? So here is that retrieval. So in this case, going to run this query, how it will give you the output. Let's see. So create table created, index also HNSW index created, gen index created. So with order embedding, it is showing the output chunks first 80 characters. So you can see these are all the chunks. So these 5 chunks pass as a context to your LLM prompt grounded answer. So RAG retrieval hybrid RR eliminates pinecone for most use cases. Okay. So this is how it is working that pipeline retrieval augmented generation. And coming to this capability number 6, PGML. In this is in database ML interface, PGML inference, right? In database ML inference with the PGML, it is using PGML underscore dot predict PGML underscore embed train in SQL zero network hook. Okay. So in database ML inference PostgreSQL machine learning, this is most impressive capability on this list instead of running a Python ML service that your application has to call. The trained model lives inside PostgreSQL and you call it with SQL. PG underscore dot embed generates embeddings from text without a Python. PGML and dot predict runs trained model inference. You can deploy a fraud detection model and run it against every incoming transaction with a single SQL where class, no REST API, no serialization, no network hop. The model and data are in the same process. Okay, so the ML inference in SQL deploy models once call via select, no Python service needed. PGML brings trained model inference into PostgreSQL, runs sentiment analysis, fraud detection, embeddings generation, and classification with SQL functions. The model and data are co-located, zero network serialization, overhead. PG.ml.predict replaces a Python microservice. Okay. Let's see a quick interactive demo for this pgml generate embedding in PostgreSQL, no Python needed. So there is an update in products. Set embeddings pgml embed sentence transformation on a mini lm l6 version 2 description vector where embedding is null. Okay, there is one update query, and also we are doing the set train a sentiment classifier in SQL. So select pgml.train. So the project name, task, relation name, column name, algorithm, and also real-time sentiment prediction. It is doing that another select query, and also another one fraud detection. So fraud detection, so it is performing. Okay. So let me run this demo and see how it is working. So first, while executing this one, update products, it is doing the update generating embedding via PGML in database. Update 1247 lesson and 124 products embedded without leaving PostgreSQL. Select PGML in this class will loading transformer model, training and customer reviews. Training complete, model review comes sentiment deployed, and select that PGML predict. It is also doing that review truncated sentiment confidence. So amazing sound quality, love it, positive. Battery died after 2 hours, terrible, negative. Good value for the price, positive, negative. So it is giving that three output. In database, ML predict runs without external Python service. So this is how it is working in that in database machine learning inference with the PGML in PostgreSQL. Okay. So next capability, a capability number 7, hybrid search in PostgreSQL, hybrid search and vector analytics. Okay. So PostgreSQL capabilities number 7, hybrid search and vector analytics. The real insights that vector search and full text search have complementary failure modes. Vector search is misses exact keyword matches. A product code like SKU 2847 has no useful semantic representation. Full text search misses synonyms and related concepts. Combining them with either zero weighted, a linear blend, or a reciprocal rank fusion gives you the recall of vector search with the precision of full text search. Okay, this is hybrid vector search. And vector full text combined. It is weighted linear blend RRF 70% semantics plus 30% keyword. Okay, so best for both wells. Vector search finds meaning. FTS find exact keywords. Pure vector search fails on product code. SKU hyphen 28447 has no semantic meaning. Pure FTS fails on system. Hybrid combines both semantic recall with the keyword precision. Or of the reciprocal rank fusion is the recommended combination method. It is outperforms simple score blending. Hybrid search score breakdown, query, headphone, and SKU 2847. Okay. So here's the breakdown. We'll see the product, vector score, FTS score, hybrid 7030, and winner. So wireless ANC headphone SKU 2847, it is vector score 0.91, FTS score 0.84, hybrid 7030, it is 0.888. A winner, it is best. And ANC earbuds like no SKU match. Vector score, it is 0.87, FTS score 0.12, and hybrid, it is 0.64. It is good. SKU 2847 cable wrong category. It is vector score 0.12 and FTS score 0.92 and a hybrid 7030, it is 0.30. It is low. It is USB hub SKU 8821. USB hub SKU 8821. It is vector score 0.18 and FTS score 0.04 and hybrid 7030, it is 0.138. It is filtered out. So this is that vector search exact find keywords. Okay. So let us quickly see that interactive demo and the hybrid search 7030 vector and 30 full text. So this is the select we are going to run now. Let's see. So the select query, it's coming up with this output wireless and see headphone SKU284. It is hybrid winner. Okay, Bluetooth ANC earbuds. It is vector help. Over here, studio help mode. It is 0.0 and SKU284 cable wrong type. FTS false post suppressed. So here it is a hybrid vector search. It is worked exact SQL image plus semantic relevance equal to correct top result. Okay, this is how that hybrid search vector plus full text combined search is working for us. Yeah, hybrid search. Okay, it is capability AI capability number 7, and finally we are going to see that AI capabilities number 8, vector analytics. Vector analytics, you can compute a semantic centroid, a category, detect outlier products that do not belong in their category, find near duplicate documents, and measure cluster cohesion all in SQL. Okay. So vector analytics and AI insights, it is using the semantic centroids, outlier detection, duplicates detection, cluster analysis. So here SQL in vector space, analytics that were impossible before pgvector. Compute that semantic centroid a product category, deducts outlier in product MIS categories, find near duplicate products with greater than 95% similarity, measure how cohesive each category is, all in SQL, no Python, no Jupyter, no external ML pipeline. Okay. So semantic centroid average embedding vector computes the mean vector of group, a semantic center of gravity of a category, compare categories to measure semantic overlap. Outlier detection products from their category centroid may be miscategorized. Similarity less than 0.42, centroid equal to flag to review. Automate catalog quality control. Duplicate detection. Products with greater than 0.95 in similarity or near duplicates. Find catalog redundancy automatically without manual review, and cluster cohesion. Measure how semantically tight each category is low. Low cohesion equal to category needs splitting. High cohesion equal to well-defined product group. Okay. So here we will see a quick select query. How it is the analytics and AI insights work on this. Okay, and let me run. Let's see that output. So here, select query, it is working. So it is doing the search and access that how location speed this category. With this, how to use that. So vector analytics tool is categorized product detected automatically. So here to detect automatically, right? So production use run the centroid plus conversion query weekly as a catalog. Quickly check product with the similarity less than 0.42. Their category centroid are automatically flagged for recategorization review. This replaced 40 plus hours per month of manual catalog review at one e-commerce client. Okay, so this is what we have uh, discussed for that PostgreSQL AI capabilities. And so the unified AI database, let me end with this architecture comparison. Traditional AI stack, PostgreSQL for relational data, Pinecone for vector, Elasticsearch for full text, Redis for fuzzy autocomplete, Python ML service for inference, 5 system, 5 billing accounts, 5 failure points, and endless problem of keeping them in sync. PostgreSQL AI stack, one database, one connection, as it consistency, unified backups, unified monitoring. pgvector replaces minecode. Native FTS replaces Elasticsearch for most use cases. pg underscore trgm replaces Redis autocomplete. pgml replaces that Python ML service. If you are building a new AI application, start with PostgreSQL. You will add the dedicated vector database later if you actually need it, and most teams never do. All the SQL from this video is on my blog is at aadbhub.com. So subscribe for more PostgreSQL tape time, and for my upcoming videos, I will show you more AI capabilities demonstration with a live demonstration. Okay. Thanks for watching Oracle Excellence AIDB Hub channel.